This second lecture is our opportunity to venture into the laws, the rules that govern the world of the nanoscale, the physical principles, the chemistry. It's also our chance to get reacquainted with the particles, the building blocks of the nanoworld, atoms and molecules that make materials, photons, light that conveys energy. It's our chance to think about how the properties of these materials, the way in which they bind, their shape, their structure, influences how we experience them, how the nanoscopic translates into the macroscopic. And finally, it's our opportunity to think about how some of the specific rules of the game are changed at the nanometer length scale, how quantum effects start to become important. They start to become something we can actually engineer with. Let's start in on the materials and their constituents. Here's how we visualize an atom. It's an approximate picture, and we'll go into more detail about the approximations and how to make this more precise. But to start with, we often just picture it as like a planet with electrons orbiting it. The planet itself is the core, it's the nucleus of the atom, and it consists of a combination of protons having positive charge and neutrons, which are neutral. As nanotechnologists, we often think of electrons as our building block. We think of atoms surrounded by electrons as the next layer up. And we tend to focus on the electric fields and the magnetic fields that behave. And so we're focused on these particular forces rather than what people refer to as the subatomic or subnuclear behaviors that reside in the field of particle physics. So we distill the behavior of electrons in this way. We distill the behavior of atoms in this fashion. So what ends up mattering to us principally is the fact that the core, the nucleus, has its positive charge. That is attractive to the electrons having their negative charge. Now, the way in which the periodic table is formed maps onto this description of shells. We think of these satellites, these electrons that orbit the nucleus, as being able to occupy one of a number of gradually increasing energy levels. They're able to fill up these regions where the electrons are allowed to orbit. And depending on how full each of those shells is, that will determine which column of the periodic table an atom resides in. And the column of the periodic table that it resides in turn, determines the personality of that atom. Atoms or elements in the same column have quite similar chemical behaviors often. So, for example, in the first column, we have things like sodium and lithium that have a single electron in their outermost shell. That outermost shell, these valence electrons that populate this outermost shell, they're the key ones that relate to chemical reactivity. So we pay most heed to them when we're thinking about materials being built up from such elements or atoms. And in the case of this first column, because atoms love to have their shells completed, those atoms that go around with one electron available to participate in bonding, they represent an opportunity from the point of view of those atoms having a shell that's almost complete. And so table salt, sodium chloride, consists of sodium having a single valence electron, chlorine having 7 valence electrons. When they form a complete shell together, 8 being complete, they're satisfied. Chemical bonding has occurred in a fashion that achieves stability. Now, the other thing to note about this example of bonding between something far on the left of the periodic table and something far on the right is that it's a very asymmetric relationship. It's one that involves polarity. There's a preference for the movement of electrons in one direction or the other. It's called ionic bonding. There's another kind of bonding that is crucial and, in fact, is much stronger. And it's a kind that occurs based on sharing. And the kinds of atoms or elements that are most prone to this sharing or covalent bonding are those more in the middle of the periodic table. And here is where there's some very important materials that we'll see many times throughout this course. Silicon is a great example. Carbon is also in the middle of the periodic table in group 4. And group 4 means that it has 4 electrons available to participate in bonding, and it's got 4 missing in order to form a complete shell. And these materials that are sort of halfway through, they're going to form symmetric relationships with each other. And so, for example, the silicon and the carbon lattices form materials based on this very strong covalent force and based on sharing. And they form materials that are extremely stable. So if you look at the diamond lattice, every carbon atom will be participating in bonding with 4 nearest neighbors. And through that sharing with 4 nearest neighbors, every one of them will feel complete. It will feel that it has its shell completed. We'll invoke these ideas from the periodic table relating to the feeling of completeness by atoms, the propensities they have to pair with one another throughout this course. The bonding of atoms with one another is obviously one of the central tenets from which we build up materials. So far, though, when we talk about things like diamond or silicon, that crucially important electronic semiconductor material, we're thinking of almost infinite arrays of atoms, periodically arrayed, forming a very systematic behavior that's common throughout the entire solid. And when we think about those materials as well, we will eventually arrive at an interface. They're not infinite materials. Eventually, a piece of silicon will have an end to it. It will have an interface. And there we'll become very concerned with the management of that interface. Another way to say that is that these materials that rely on this long-distance periodicity and coherence, when we do reach an interface, we have to manage the interface. They're not a self-contained material. In contrast with that, molecules are combinations of atoms where the binding amongst the atoms is completely satisfying to that structure. It's a self-contained structure. There's, of course, many famous molecules that we're very well acquainted with. Water, H2O, is one of them. Oxygen in the air we breathe is, in fact, molecular oxygen, O2, where the 2 oxygens can satisfy one another in a nice strongly bound pair. Some of the much larger molecules that we'll discuss throughout this course, things like DNA and proteins, the sugars that make up our bodies, the sugars that are generated as a consequence of the process of photosynthesis. These are all molecules that achieve these relatively stable conformations. Things like buckyballs, bucky tubes are also these structures that are satisfied with their binding within themselves. Now, we've spoken about the building blocks of matter. We've spoken about things that have appreciable mass. What about energy? How is it conveyed? Well, we'll start in on this discussion of energy, color, and spectrum from a wave perspective, from the point of view of electromagnetic radiation as a picture for light. But then we'll also realize that there's more to the picture of light than just this classical picture, this wave picture, that we also need to start thinking within the vocabulary of photons, particles of light. So let's start and just see what we can get out of this wave picture. So the wave picture of photons of electromagnetic radiation has an oscillation of an electric field and of a magnetic field. In fact, if we think of a single pure color, I'll call that monochromatic light, then the electric field oscillates with a defined period in space and in time. And that period in space is referred to as the wavelength. And so let's take a couple of examples. The visible light that we can see with our own eyes, this has wavelengths characteristically in the range of 400 to about 650 or 700 nanometers. So it's measured in the nanometers, but it's getting close to the micrometer length scale. That property of light, of visible light, ends up being very important because it turns out that a wave is difficult to condense or to shrink down to a length scale that's smaller than its own wavelength. We're able to maybe tie the 2 ends of a string down at a spacing of a wavelength or a half a wavelength, but we're not able to do much better than that. And so the wavelength of an electromagnetic wave will determine how well you can focus it down. And so if you think of using a traditional optical microscope to try to look at something, well, you can see cells with it, biological cells that are 10 micrometers in size. You can even see bacteria that are perhaps a few micrometers in size. It's much more difficult to see a virus that can be as small as 100 nanometers in size. That's really starting to get to the limits of what you can see using visible wavelength light. But the word visible wavelength isn't a comment on a fundamental quality of light itself. It's actually about the colors that we are particularly attuned to see. Because the sun is at a very elevated temperature, it has a very strong emission in the visible wavelength range, and our eyes are adapted to make very good use of those wavelengths. But it turns out that one can go very, very far to longer wavelengths, or much farther to shorter wavelengths. There's an incredibly broad electromagnetic spectrum. So, for example, we call visible light, but to a snake, the light that many pythons can see is actually infrared light. It corresponds to much longer wavelengths than what you and I sense. And that's actually very useful to them because infrared radiation is more of a signature of heat. And so snakes are able to sense vulnerable regions of their prey based on their infrared or thermal signatures. We can go far in the other directions towards shorter wavelengths. As we go to shorter wavelengths, now if we're using light as a tool to carve matter, or if we're using it as a tool to investigate structure, such as through a microscope, well, in that case, we're able to see with much finer spatial resolution. And so, for example, with ultraviolet light, we're able to define structures using images projected using ultraviolet light much better, much more finely using UV rays than we are able to do with visible light. And that gets even more true as we go into the regime of X-rays. Now, we've spoken about light as a wave, and that is a very useful concept as well. But Einstein is famous for many discoveries and many insights, but one of them is his ability to explain a simple but hitherto mysterious experiment called the photoelectric effect, an explanation that Einstein provided that invoked a particle-like quality to light, something where it was a packet, a unit of energy. And this photoelectric effect that Einstein was trying to explain, it was based on experiments that had been done prior to his coming along and thinking about their interpretation. The experiment was the following. It involved having a metal, one could use various different types of metal, and illuminating it with different colors of the electromagnetic spectrum. And what had been observed in the photoelectric effect is that for longer wavelengths, there was essentially no emission of electrons from this metal upon photoexcitation, so there was no photoelectric effect. And once one went to short enough wavelength, and the exact wavelength depended on the metal, but once one went to a short enough wavelength, one produced the generation or the emission of a large number of electrons. And the intensity of that collection of electrons, that photocurrent, went in proportion with the light intensity when one was above this threshold, when one was at a short enough wavelength. But for the longer wavelengths, it really didn't matter how hard you hit the material with light. It essentially didn't emit at all. And Einstein was able to provide a simple and elegant explanation that has very much stood the test of time since he proposed this in 1905 and won his Nobel Prize for it in 1921. And the explanation was that there was a certain energy that electron needed to be elevated by to escape from the metal, and that only those photons of a short enough wavelength contain sufficient individual energy. And so he started to think of the photons as quanta, or as packets of energy, and there was a direct relationship, an inverted relationship, between their wavelength and their energy. So the long wavelength ones had insufficient quantized energy available to induce the emission of an electron from this metal, whereas those at the short wavelengths had a greater quantum of energy that was able to kick that electron out of the metal. And so this then brings us to this additional dimension, or this additional property of photons that we need to pay careful heed to. When we use thermal imaging, or when the snake sees in the dark, we're actually dealing with very low energy photons. That's consistent with the fact that instead of being produced by the very hot sun, which produces higher energy photons in the visible, when we're doing thermal imaging, when we're, say, looking at a warm person against a colder background, we're actually looking at much lower energy photons corresponding to those that are realistically emitted by somebody who's just a little bit above room temperature, just a little bit above the temperature of their background. Moving to a slightly higher energy are the visible photons, the visible wavelengths, and then just beyond that, the ultraviolet. And ultraviolet rays are familiar to us because they're arriving on Earth, they're emitted by the sun, and we're concerned about their effects on us, their correlation with skin cancer. Well, the reason why ultraviolet rays are much more prone to promote skin cancer than visible wavelength rays are is because of their added energy. They're more likely to interact with DNA or proteins, various potentially reactive species in our bodies, and result in the excitation of an electron that can lead to a new reaction. It can lead to a conformation change or a chemical change inside one of our cells. And so here too, the energy aspect of light becomes very important and is central to explaining why ultraviolet rays are really qualitatively different from the way visible ones are. And then if we move further still to higher energies, we get into the X-ray regime, familiar, of course, in medical imaging. And in the case of X-rays, these are considerably more energetic. They can have 1,000 times the energy per X-ray photon compared to what we see in the visible, or even more than that. And one of the consequences is that X-ray detectors that are used now, especially in digital X-ray, digital mammography, are able to collect thousands of electrons worth of current for every photon incident upon them. So this is just a testament to the huge amount of energy contained in the X-rays. And the good news about that is that we can therefore get away with using a relatively small dose or a small abundance of X-rays when we perform medical imaging. I'd like to spend a moment now to think about a connection between materials and light, because much of our discussions in this course will relate to how we can shape nanomaterials in such a way as to emit light, reflect light, convert light into an electrical form, or vice versa. And it's interesting to note that some of the earliest nanotechnologies were simply making stained glass, long before one thought in terms of nanotechnology. Thousands of years ago, artisans were mixing paste together and forming red versus yellow stained glass, where the red versus yellow was determined as a consequence of different metal particles of different sizes that were included in the stained glass. And these different sizes of particles were able to support different resonances on them. Today we call this effect plasmonics. It refers to the idea that waves related to electromagnetic waves can be supported resonantly on a structure that fits that wavelength nicely. Whereas if there's a lack of a resonance, there will be no particularly strong interaction between the metal particle and the wave. And so stained glass is one of these early manifestations of the interaction between material and electromagnetic waves and resonances that occur at the nanoscale. It's important, as we were discussing earlier, to think about how materials' macroscopic properties, beyond just their visible, their optical properties, but also their mechanical properties, are a manifestation of what goes on at the nanometer length scale. And one way to get at this concept is to think about materials that actually are compositionally the same when you look at them in the periodic table, but that have vastly different properties as a result of different conformations or ways in which they bind together. And a good example of this is carbon. So carbon, group 4, member of the periodic table, the basis for diamond, can bind in this covalent manner that we were describing earlier, in which every carbon is satisfied. It's got a bond up and then 3 down in symmetric tetrahedral form. And diamond, of course, is an extremely hard material, and its hardness is symmetric in all directions. So because this binding occurs kind of with a spherical symmetry, there's no particular plane of vulnerability for diamond. It's strong, it's essentially in all directions. Now, graphite is also made out of carbon. Graphite is what's misnamed pencil lead, but it's the basis for how we write with pencils. And so it's also carbon-based, and constitutionally it's built up of the same elements as diamond, and yet it's so incredibly different. It's so soft, and it's opaque instead of being clear. we can't see through it. And so how can that be? Well, the effect does come down to the nanoscale structure, the way in which the carbon atoms are arrayed. In the case of graphite, the carbon atoms bond together in the plane. They form little hexagonal regions. They have 3 nearest neighbors instead of 4 within the plane. And then these planar sheets stack up on top of each other. And the interactive forces amongst the sheets are much weaker in this stacked or vertical direction than they are within the plane. And so it's very easy, whereas internally these graphene sheets are quite robust, they can slide past each other. There's nothing really keeping them from translating relative to each other. And so essentially we have a sloughing off, a flaking off of these graphene sheets that occurs in graphite. So now the material's properties are very directional, and that arises from the very different behavior, very different conformation of these materials in the plane compared to out of the plane. In fact, graphene is a nice example, carbon's a nice example as well, for many of the building blocks of nanomaterials. Buckyballs, which are little soccer balls of carbon bonded together, Bucky tubes, which are these nanotubes, and graphene itself, the planar sheet, but now at a single layer. They're all materials of great interest in nanotechnology that we'll spend quite a bit of time on in this course. Another thing to think about in graphene is that its electronic and optical properties are so different from diamonds. Diamond is this transparent material, which is related to the fact that its bonding is so strong that there are very few low energy transitions available to it. So it doesn't absorb low energy or even medium energy photons like visible ones. You need to go well into the ultraviolet to excite transition within diamond and therefore to have optical absorption. Whereas in graphite, graphene, and related materials, these are in fact essentially conductors, and they have an abundance of electrons available to participate in the process of electronic flow and also to participate in the process of optical absorption at a wide range of wavelengths. We've alluded to the fact that quantum effects play a major role in the behavior of nanomaterials, and that there's something that we need to understand. In fact, one of the exciting regimes within nanotechnology is to explore how we can use nanostructured materials and the quantum effects that emerge on these length scales in order to control the behavior of matter, to create materials having new custom or designer properties. And here there's an interesting class of materials called quantum dots that take advantage of these properties of the wave-like nature of atoms. But to spend a moment just to understand this wave-like behavior, we should just take some time to look at how an electron actually configures itself. In the quantum world, we no longer can think of electrons just as points, the way we were trying to depict them in this cartoon at the beginning of this lecture. We're trying to think of them as very small point satellites orbiting their nucleus. But in fact, quantum mechanics and in general the concept of wave-particle duality tells us that just as we began thinking of photons as waves, but then we had to consider their quantum behavior, it's also true for electrons, which we're inclined to think of as points, we're inclined to think of as particles. Well, they also have a spatial extent, and that spatial extent is on the scale of a couple of nanometers. Take a look at this picture of the distribution of an electron wave. It can be a very simple one. It can just be sort of a parabolic shape that's very smooth. But electrons can actually take on resonances with the materials that they exist in. They can take on very complex wavy structures. But the thing to remember about electrons is that whereas with photons, it's their wavelength, say for the visible ones, in the hundreds of nanometers that we're interacting with, where we have to really think of them as waves. With electrons, we need to think of them as waves once we get down to the scale of a few nanometers. And so quantum dots are an example of some particles, a class of semiconductor materials that we'll definitely see a few times throughout this course that are leveraging, are taking advantage of the wave-like properties of matter. You see here a bunch of beakers filled with semiconductor particles, all of the same underlying composition. They all have the same elements inside them, but you can see that they're all glowing different colors. And the reason for that is that these particles are all of different sizes. The ones on the left are 2 nanometers in diameter, the ones on the right are 5 nanometers in diameter, and the ones in between are of sizes in between. And what happens in the very small particles is that we've confined this electron wave, which would like to be free. It would like to be delocalized. It would like to expand its territory within the semiconductor, but we've confined it by making a very small particle, essentially a box, into which we've trapped the electron. And as a result, we've pushed up its energy levels. On the rightmost beaker, they have these nanoparticles that are considerably larger. We're squeezing our electron wave less, and it's able to occupy a lower energy level as a result of that. And so using these quantum effects, leveraging the wave-like properties of matter, we found a way to engineer or make a tunable semiconductor. These quantum properties of materials, the unavoidable wave-like nature of the electron, it leads to this idea of localization and the fact that we can tune a material in this fashion. It also leads to a very curious phenomenon that's known as quantum tunneling. Quantum tunneling can be described first by saying, how would an electron behave if it was only to be thought of as a particle? Well, if an electron were coming along and it were just a particle and it would see a wall or a barrier, and that barrier was of an energetic height that the electron could not climb over, then it would simply reflect back. Now, in the world of waves, though, this electron isn't just a discrete particle. It has a spatial extent. And when that electron arrives at this boundary, even if it doesn't have sufficient energy to overcome it, there's some probability that the electron will find itself on the far side of that structure. It would be more like an electromagnetic wave seeing, say, a piece of glass at a particular angle and having some chance of making it through, some being reflected, but some of it making it through. And so the same wave-like phenomena start to occur for electrons. And so we have these confinement ideas, like the plasmonics for photons. We have electron confinement inside a quantum dot. And then we also have these possibilities of different kinds of interactions with materials, partial transmission of a wave through a material and partial reflection of it. And these are things that we see when we get down to the quantum length scale. They're properties of electrons that we only need to heed, we only need to pay attention to once we get down to this scale. You know, the other really intriguing thing about these quantum dots is that they actually are another manifestation of our periodic table concept, but now another layer up. It's not the atoms themselves that now in these quantum dots is periodic table-like, but it's once we put them together, we make a semiconductor having a single set of fundamental properties, but then we change the size. It's like scanning across or down the periodic table, where we change the energies, we change the amount of pull that the electrons see, keeping them confined, just the way when we change the number of protons in the nucleus of a given atom or element, we change the potential that it sees. And as a consequence of this, people refer to quantum dots as artificial atoms. They're an analogy with the periodic table, and really what they allow nanotechnologists to do is to build up a kind of periodic supertable, a new set of atom-like materials that go beyond the properties of their constituent atoms and that add another layer of complexity, another layer of tailoring or engineering. So to finish this lecture, just reviewing some of the concepts that we'll use throughout this course, also some of the ideas that we'll use. One of the central tenets, really, is that the behavior of the macroscopic world around us, even if it's not typically nanometer scale in which we think of ourselves as interacting with the world, objects are hard, they're heavy, they have certain colors, well, that in fact their properties do emerge from the nanoscale, their morphology, the ways in which atoms are arrayed at the nanoscale, the bonding amongst these atoms, whether there's a directional nature to that bonding, an alignment, whether these materials have shape. These underlying nanoscale properties all influence the macroscopic behaviors. In addition, there are nanospecific concepts that we need to pay attention to when we're engineering within the quantum world. And in fact, this is where a great deal of the opportunity for nanoscale engineering lies. Concepts like the confinement of electron waves, the fact that electron waves can tunnel through a structure which classically it would not be able to, the fact that electrons are delocalized in semiconductors, the fact that they form waves that can propagate, convey electrical information, electrical energy, and then also the fact that in nanostructured materials we have an abundance of surfaces. These are all concepts and they're all tools that we'll be using to engineer at the nanoscale.